Hello friends, welcome to my lecture on trees. A connected graph without any circuit or cycle, okay, circuit is also called cycle. So, a connected graph without any circuit is called a tree. For example, you can look at this graph, it is a tree, okay. You can see there is no cycle in this, but if you look at this graph, there is a cycle here. You can see, you can start from here, you can follow this path and you can come back here. So, there is a cycle in this graph and therefore, it is not a tree. This graph is however a tree, because there is no circuit in this graph and it is a connected graph. Now, let us see this ones. This is a tree with one vertex, this is a tree with two vertices, this is a tree with three vertices, this is a tree with four vertices and this is another tree with four vertices. Okay. Now, parallel edges and self loops both form circuits, and therefore, a tree cannot have parallel edges and self loops. Thus, a tree has to be a simple graph. A graph G is a tree if and only if there is one and only one path between any two vertices of G. First, let us suppose that the graph is a tree. Then, by definition of a tree, G is a connected graph. We have said that a connected graph is called a tree if it has no cycle. Okay, if it has no cycle, a connected graph without any circuit or cycle is called a tree. So, if the graph is a tree, then by definition of a tree, G is a connected graph. Therefore, there must exist at least one path. If it is a connected graph, there must exist at least one path between any two vertices in G. Now, suppose that there are two distinct paths between vertices A and B of G. Okay. Then, the union of these two paths will contain a circuit and G cannot be a tree. Okay. So, there is only one and only one path between any two vertices of G. Conversely, suppose that there is one and only one path between any two vertices of G, let us show that G is a tree. Okay. Since there exists a path between any two vertices of G, therefore, G is connected. So, first thing we have shown is that G is a connected graph. Now, let us show that it is without any circuit. So, a circuit in a graph G with two or more vertices implies that there exists a pair of vertices A and B such that there are two distinct paths between A and B. Okay. That is the meaning of circuit. Okay. So, since G has one and only one path between two vertices, G can have no circuit and therefore, G must be a tree. Now, let us go to this theorem. G be a finite graph, let G be a finite graph n greater than with n greater than 1 vertices. Then, if G is a finite graph with n greater than 1 vertices, then the following are equivalent. G is a tree implies and implied by G is cycle free and has n minus 1 edges. Okay. Now, G is a tree means it is a connected graph and it is without any circuit, connected graph without any circuit. So, it is cycle free, without any circuit means it is cycle free and moreover it is connected. So, every vertex between any two vertex there is an edge, one and only one edge. Okay. Therefore, it has n minus 1 edges. Okay. And now, 2 implies 3. So, 1 implies 2, 2 implies 3, 2 implies 3 because G is cycle free and has n minus 1 edges. So, G is connected and cycle free and has n minus 1 edges means you take any two vertices. Okay. Okay. So, it has n minus 1 edges, n minus 1 edges means that between any two vertices there cannot be more than one edge. Okay. So, there are n vertices there are n minus 1 edges, therefore, between any two vertices there is an edge. So, G is connected and has n minus 1 edges. Okay. And if G is connected and has n minus 1 edges, then G is a tree. Now, every tree with two or more vertices, if you take any tree with two or more vertices, it is 2 chromatic. That means, if you take a tree with two vertices or more than two vertices, it can be painted with 2 colors. Okay. Minimum number of colors that can be used to paint this tree will be 2. Okay. So, let T be a tree and B be any vertex in T. Okay. B be any vertex in T. So, let us say this be a vertex. Okay. Assign color 1, color 1 we can assign to this vertex, assign all the P vertices adjacent to B with color 2. Okay. Say suppose this is like this. Okay. So, and then it is like this. So, this one is, and then you can say this one, okay, and this one, Okay. So, let us say this is B, this but this vertex. Okay. This vertex is adjacent to this one, so it will be painted with color 2, and this vertex is adjacent to this vertex, so it will be painted with color 2, and then this vertex is adjacent to 2, it will be painted with color 1. This vertex is adjacent to 2, so it will be painted with color 1, and here this vertex is adjacent to this vertex, so it will be painted with color 1, and this is also adjacent to this, so it will be painted with color 1. So, 2 colors are required to paint a tree, okay, with 2 or more vertices. If there are only 2 vertices, okay, then you have a graph, you have this graph, okay, which is a tree. Okay. So, in such case one color will be needed for to color this, and one color will be needed to color this. So, 2 colors are required if tree has 2 vertices, and if it has more than 2 vertices, then you need again 2 colors only to color it. Okay. So, so assign all the p vertices adjacent to B with color 2 and assign color 1 to all vertices adjacent to the vertices of color 2, like we have done here. Continuing the process till every vertex in T is colored. Since there is one and only one path between any 2 vertices in a tree, no 2 adjacent vertices will have the same color. Okay. So, T has been properly colored with 2 colors. Since T has at least 2 vertices, okay, so we will it will have at least one edge, and therefore, one color will not be enough, hence therefore, T is 2 chromatic. Now, let us, so this one we have, this is vertex B, okay. This vertex is adjacent to B, so it is colored with color 2. B is colored with color 1, it is colored with color 2. This vertex is adjacent to this vertex B, so it is also colored with color 2. Now, this is adjacent to this vertex, so it is colored with color 1. This is adjacent to this vertex, so it is also colored with color 1. Here this vertex is adjacent to this, and it is colored with 1, so it will be colored with 2, and then this is adjacent to this, so it will be colored with 1. This is adjacent to this, so it is colored with 2, and this is adjacent to this, it will be colored with 2. So, you can see the entire tree can be colored with just 2 colors. Now, converse of the above theorem is true, that is to say, if a graph is 2 chromatic, okay, if a graph is 2 chromatic, it need not be a tree. Okay. So, for example, this one, you can see this graph. Okay. This graph with 4 vertices, you can see this is a here we are using 2 colors to color the vertices of this graph. This is colored with color 1, this colored with color 2, this colored with color 1, this colored with color 2. So, adjacent vertices have different colors. Okay. Now, so it is a 2 chromatic chromatic number here is 2, okay, chi g equal to 2, but you can see it is not a tree, because there is between any 2 vertices there must be one and only one path, but here you can see, suppose you take this vertex, okay, then you have one path is this path, okay. One path is AB, the other path is this one AB, AC, CD, DV. Okay. So, that is another path between A and B. So, there is not one and only one path between any 2 vertices here, therefore, this is not a tree, or you can see it is a cycle. You can start with A, you can go along AC, then CD, then DV, you can come along BA back to A. So, it is also a cycle, and therefore, it is not it is a connected graph, but it is not a cycle. It is a cycle. So, a connected graph without any cycle is called a tree, and here it is a connected graph with a cycle. So, it is not a tree. So, a 2 chromatic a graph which is 2 chromatic need not be a tree. Now, let us consider a subgraph T of a graph G. Okay. A subgraph T of a graph G is called a spanning tree if T is a tree and T includes all the vertices of G. You can see this graph. Okay. There are 6 and 3, 9 vertices. Okay. So, vertices, number of vertices is 9. Now, let us consider a spanning tree. A spanning tree means a tree which has n vertices, all the vertices of this graph, okay, and it is a tree. Now, you can see here it is not a tree. It is not a tree because between any 2 vertices there does not exist one and only one path. So, it is not a tree. Okay. We will find a spanning tree here, that is a graph which has all these n vertices and it is a tree. So, let us see this one. You can see this graph, it has all n vertices and 9 vertices you can see, and we have come to this graph by removing the edge, these ones. We have removed this edge has been removed, okay, and these edges have been removed, this edge and this edge. Okay. So, and moreover this edge is also removed, this one. Okay. So, we have removed this one, we have removed this one, we have removed this one, and we have removed this one, and we have removed this one. Okay. Yeah, and also this one. So, this okay, this okay, this one has been removed, this one has been removed, this one has been removed, this one and this one and this one. Okay. So, these edges are removed and we come to this. Now, you can see between any two vertices there is one and only one path. Okay. Suppose you take this one, these two vertices, there is one and only one path. Between these two there is only one path, and this is always only one path. Okay. There is only one path between any two vertices here. So, this is a tree and it has number of vertices is 9. So, it is a spanning tree. Okay. Now, here let us look at the other figure. This is also a figure obtained from here. Okay. So, we have this we have removed this one, we have removed this one we have removed. Okay. And then we have removed this one we have removed. Okay. This one we have removed, and then we have removed this one, okay, and we have removed this one and this one. Okay. So, after removing these edges we reach here. Okay. And you can see now between any two vertices here there is one and only one path. Okay. So, and it includes all the n vertices here. So, it is also a spanning tree. So, two possible spanning trees are given here. Now, minimal spanning tree, suppose G is a graph whose edges are assigned lengths. Okay. Here you can see a graph whose edges are assigned lengths, that is are labelled with positive numbers. T is called a minimal spanning tree if among all the spanning trees of G, T has a smallest sum length. The labelled graph G in figure given below has 3 spanning trees. We have 3 spanning trees. The first part is find the spanning trees of G and their lengths, which is the minimal spanning tree of G. So, you can see there are 3 minimal spanning there are 3 trees here which are spanning trees. Okay. And we can find the lengths of each of these trees and then see which one has the minimum sum length. Okay. So, we have this graph. Okay. So, let us draw the graph here. So, 2, 6, 2, 3, 3, 1. Okay. Now, so this one has length 2, this one has length 6, this one has length 2, okay. This one has length 3, this one has length 1. Okay. We have removed this edge, okay, to reach here. Okay. And then we have consider this one, we have removed this edge to get this one, and we have removed this edge to get this one. Okay. So, we have 2, 3, we have 2, 3, 1, and then we have here 2, 6, 3, 3, 1. Okay. So, let us find the minimum length. Okay. 2 plus 6 plus 2 plus 3 plus 1. So, T1 has 1, 3, 4, 4 to 6, 6, 12 and then 2, 14. Okay. So, some length here is 14, here 2 plus 3, 5, 5 plus 2, 7 plus 3, 10 and then 11. So, T2 has length, some length 11 and here 2 plus 3, 5 plus 6, 11 plus 3, 14 plus 1, 15. So, T2 has the minimum sum length. Minimum sum length. So, minimal spanning tree. Okay. They are all minimal, they are all spanning trees, but T2 has the smallest sum length. Okay. T2 has smallest sum length and therefore, T2 is the minimal spanning tree. So, for the given graph we first find all the spanning trees and then calculate the sum lengths. So, then we will find out the smallest sum length. The spanning tree for which we get the smallest sum length is then will then be the minimal spanning tree. So, that is the end of my lecture. Thank you very much for your attention.